new section, and the section name is Implicit Differentiation and Rational Exponents. We will come to this rational exponents part afterwards. Let us first see what implicit differentiation is. And we are going to start our discussion with this equation: x cubed plus y cubed minus 9xy equals 0. If you draw the graph of this equation, this is what you get. I mean, you understand that the graph extends indefinitely on that side as well as on this side. So you are looking at that portion of the graph which is near the origin, and there is a loop. But this is not the graph of a single function because it fails the vertical line test. You consider this vertical line. This line intersects the graph at these 3 points, which means that it of course cannot be the graph of a function. That is because for a given input value x0, a function should only give you one output value, and accordingly there should only be 1 point on the graph of the function. Here, however, you are seeing 3 points. Okay. However, it is the union of the graphs of 3 different functions. One of them is some function f1 whose graph is the upper part of this loop between O and A, this one. Another function is f2 whose graph starts from A here and extends indefinitely on that side, that means this one. And there is another function f3 whose graph starts from O and extends indefinitely on that side. These individual curves, which are parts of this entire thing, are graphs of some functions. Now you note that the entire graph has a well-defined slope at nearly every point, which means that at almost every point you have a non-vertical tangent. Actually, you have a tangent at any point, but there are 2 points, namely O and A, at which the tangents are vertical. Any vertical line has infinite slope, so those are the points where slopes are infinite. At other points, the slopes have some finite values and they exist. And that slope, of course, you know, is given by derivative, dy dx. Alright, now it is extremely difficult to find these functions, f1, f2, f3. Well, difficulty is a relative term. I mean, if someone wants, someone can try to find these 3 functions f1, f2, f3, trying to solve this equation for y, expressing it in terms of x, but that's a different matter. Okay, and you do not solve this for y in terms of x readily, that's what I am saying. So whatever functions you have here, f1, f2 and f3, which together give you the entire curve, they are hidden inside this equation and they cannot be found so easily. So in such a situation, what will you do if you have to calculate the slope of this curve, say at this point? It will be dy dx, but you don't really know what function y is as a function of x. It is f2, but what is f2? So what will you do in that case? Are you entirely unable to find dy dx, or is there some way to really get dy dx without having to find f2 explicitly? And yes, that is possible. And that is possible because you can differentiate both sides of this equation with respect to x, treating y as a function of x. What function we don't know, but y as a differentiable function of x, and you do the differentiation using all your differentiation rules, including the chain rule, and that way you will get dy dx in that equation. I mean, after doing the differentiation, you will get another equation. There you will have dy dx, and then you solve for dy dx in that equation in terms of x and y. So on one side you will have dy dx, on the other side you will have an expression involving x and y. Using that, you can calculate slope dy dx at any given point x comma y on the curve. For example, if your point is x0, then depending on which point you are considering here, x0 comma y1 or x0 comma y2 or x0 comma y3, your slope value will be calculated using the right hand side expression, which is an expression involving x and y, and the left hand side is dy dx. So this process of finding dy dx from a given equation like this without knowing what the underlying function is called implicit differentiation. What we normally do is we are given a function, we know what function we are dealing with, and then we differentiate it. That is explicit differentiation. This is implicit because the function is hidden inside the equation. So let us now do it for this equation and let's see what we get. So you do differentiation on both sides with respect to x. And of course, first of all, you have to apply the sum rule and difference rule. So that way, the derivative of this entire left hand side with respect to x becomes this: d dx of x cube plus d dx of y cube minus d dx of 9xy. And the right hand side is 0, which is constant, so its derivative with respect to x is also 0. And now I have to use this space. The diagram we have already seen, so we can erase it. So we continue our calculation. D dx of x cube, of course, is 3x squared by the power rule. How will you differentiate y cube? Note that this is a composite function. It's the cube of y, which itself is a function of x. So that means you have to apply the chain rule here. The outer room is the cube room. If you differentiate that, again you have to use the power rule. So you get 3y squared. Okay, and there you keep the inner room y intact, and then you multiply the thing by the derivative of the inner room dy dx minus, by the constant multiple rule, 9 comes outside, and then you have to use the product rule to differentiate xy, again keeping in mind that y is the function of x. If you keep y intact and differentiate x, then you are getting minus 9y minus 9, and then you keep x intact and differentiate y. So that way you get minus 9x times dy dx. And then you can see that two terms have dy dx, 3y squared minus 9x times dy dx. And if you push the others to this side, then they become, you have minus 9y on this side, so it will be 9y minus 3x squared. And then you can divide by this. So that way, on one side you have dy dx, on the other side you have an expression involving x and y, a function of x and y both. Using this, you can calculate the slope of that curve at any given point x comma y, if it can be calculated. Note one thing, that at the origin where both x and y are 0, which is also a point on the curve, this cannot be calculated. That is because there the tangent is vertical, so slope is infinite. At other points you can calculate the slope and it will have finite value, except for that one other point A, we called it A. Now let us see some more examples of this process. So we next have example 1, which asks us to find dy dx from this equation, y squared equals x. Now if you draw the graph of this, you get this parabola. So this is not the graph of a single function of x. That is because this one also, like the previous one, fails the vertical line test at almost every point. You think of any vertical line, it intersects the graph at 2 points, except of course the origin, that is just a single case. So it is instead the union of the graphs of two different functions. So see, there is a difference between the previous equation and this one. Unlike how complicated the previous equation was, this one is somewhat manageable and we can actually find those functions in this case, so that their graphs give this entire graph. And those two functions you can clearly see are the positive square root of x and negative square root of x. So this equation gives rise to these two functions, y1 which is the square root of x, positive square root of x, and y2 which is the negative square root of x. And the domain of course is the set of all non-negative real numbers. Okay. Now because we have found the functions, let us actually differentiate these functions at any positive real number. Explicit differentiation, our ordinary differentiation. And then we will also do implicit differentiation on this equation itself. So that way also we will get dy dx, and from explicit differentiation also we are going to get derivative, and then we will match them and see if we are really getting the same thing. Okay, so these are the derivatives. You already know what you get when you differentiate square root of x. 1 divided by 2 times root x. We did this before. And this one is just the negative of that. So dy2 dx is this. And these rules are applicable only at a positive real number because x is appearing in the denominator. And geometrically also it makes sense because the tangent to this curve at the origin exists, but it is vertical. So slope is infinite. At other points, slope is not infinite of tangents. Tangent exists at every point, but that is the only point where the slope is infinite. So that's why we need x to be greater than 0 here. Okay, now let's do implicit differentiation to that equation. So implicitly differentiating both sides of that equation y square equals x with respect to x, this is what we get. And you already know how you have to differentiate the left hand side using the chain rule. So using the power rule, first you get 2y and then multiply that by dy dx, the derivative of the inner rule. And the right hand side of course is 1, and that gives you this, dy dx equals 1 divided by 2y. Here you did not have to take care of the fact that you are differentiating this one or this one. You are just differentiating y, assuming that it's a differentiable function of x. It may be this one, it may be this one. Now the question is this, are we really getting the same thing? Let's see. You can write y1 here because that's what the function is. So you are getting 1 divided by 2y1, which matches with that. What about this one? This is minus root x. Yes. If you bring this minus over to this one along with root x, if you keep it, then here you are getting 1 divided by 2y2. So it matches. Simply calculating this is enough instead of calculating these things separately. Next we have example 2, where we have to find the slope of the circle x squared plus y squared equals 25 at the point 3, minus 4. So again we have an equation, not a function, and functions are hidden in this equation. But at the same time we can find those functions. It's not really that difficult. And that is why here also, like the previous example, we are going to find the slope in two different ways. We will first find a function whose graph has this point 3, minus 4. We will differentiate it explicitly and find the slope at that point. And then we will also do it implicitly. Now before we start our calculation, we can see the situation geometrically. this is the circle, x squared plus y squared equals 25. So you already know these things from analytic geometry. The center is at the origin and the radius is 5 because it's 5 square. So you have 5 on this side minus 5 on that side. And the given point lies on the circle here in the fourth quadrant. At that point we have to find the slope, which is also the slope of the tangent. Now the two functions whose graphs you are looking at here are these, which of course you can find from here by solving for y in terms of x. So y squared will be 25 minus x squared, and then you can take square root, which is either positive or negative. So accordingly you can see that the upper semicircle is the graph of this one, y1, and the lower semicircle is the graph of y2. So we have to differentiate this explicitly and find its value at the point x equal to 3. So we find dy to dx, and to do this differentiation, of course you have to apply the chain rule, because square root is there and inside there is another function. So you are looking at a composite function. The outer room is the square root room. So minus of course is already there. Now if you differentiate the outer room keeping the inner room intact, that's how you do differentiation using chain rule. Then this is what you get. Just now you did that. ddx of square root of x is 1 divided by 2 root x. So minus is there, 1 divided by 2 times this. And then multiply it by the derivative of the inner room, 25 minus x square. And if you do this differentiation, from 25 you are going to get 0. From minus x square you will get minus 2x. 2 and 2 will cancel out, minus and minus will become plus, and this is your derivative. At any point, but which point? At any point x in this open interval minus 5 comma 5. Why this closed interval here and why do we have open interval here? You do understand that here we have the closed interval because if you take any real number outside this closed interval, then x square will be greater than 25, making 25 minus x square negative. So its square root will be a non-real complex number, but y is not a complex number. That is why the domain of the domains of both these functions is this closed interval. However, when you are differentiating, note that the tangents to this circle or to the, because we are only differentiating this one, the tangents to this lower part of the circle at these extremities are vertical. So their slope is infinite. In order to avoid that, we do not include minus 5 and 5. Elsewhere there is some slope which is finite. Now we have to calculate the slope value when x is 3. So we have this 3 divided by square root of 25 minus 3 square. 3 square is 9, 25 minus 9 is 16, square root of 16 is 4. So the slope is 3 divided by 4. And note that it makes sense also because that point was in the fourth quadrant and the tangent was like this, a positively tilted line, not like this. So slope is positive, so it's matching. And now next we do this same thing but with implicit differentiation. So we differentiate the equation of the circle implicitly on both sides with respect to x. The left hand side of course by the sum rule becomes ddx of x square plus ddx of y square, and the right hand side is ddx of 25 because 25 is constant, so that is 0. And this one by the power rule is 2x, this one by the chain rule along with the power rule is 2y dy dx. And then after solving for dy dx, this is what we get, minus x divided by y. And then we calculate the value of this slope at the point 3 comma minus 4. Note carefully that here the right hand side has both x and y and we need both the values. So we put them and we get the same value. So this one is much simpler, and another advantage is that you do not really have to see which of the explicit functions you should differentiate. There we have to decide that it's the lower semicircle, because there only the point 3 comma minus 4 lied on the curve. Here however we do not have to worry about those things. We can just simply do implicit differentiation, find dy dx and then calculate it at the point and we get slope. But these things raise a fundamental question. We have been differentiating equations implicitly, right, which are relations involving x and y from which you cannot so easily find y as a function of x. All those equations have this general form, f of x comma y equal to 0. So your function that you really want to differentiate is hidden inside this equation. And the question is this: when is a function y equals f of x determined by the above equation differentiable? What if this function is not differentiable then? So there should be some condition on the equation itself that will ensure that we are not doing differentiation carelessly. That if we follow implicit differentiation, we will get dy dx, but at the same time dy dx exists, and those conditions now I will write. These are the conditions. That function capital F, which is a function of two real variables. So far we have been considering only functions of one variable which are real valued. This is a real valued function of two real variables. It should be continuous. We don't yet know what this even means, but let's see the other conditions. These are partial derivatives. This one, for example, is like the derivative of this function if you differentiate it with respect to x, keeping y constant. This is also something we are yet to see. It will come, but we still are far away from it. These partial derivatives themselves are also functions of x and y. They should also be continuous, and the partial derivative with respect to y should be non-zero. So under such conditions, it is ensured that whatever function f this one determines, this equation determines, will be a differentiable function of x. It's some result from advanced calculus. We should not really worry about it too much at this stage. I mean, it's just given, and the things that we will be asked to differentiate implicitly will satisfy these conditions. We will see afterwards what these things are. Instead, let us next see example 3. Again, we are given an equation and we have to find dy dx. From this, the equation involves x and y, and you can see that you cannot really think of any simple way of solving y as a function of x from here. You have sin y and you also have y separately outside. So implicit differentiation is the only way to go. So we differentiate both sides with respect to x. The left hand side is d dx of 2y, and the right hand side by the sum rule is d dx of x square plus d dx of sin y. By the constant multiple rule, 2 comes outside and you have dy dx. By the power rule, d dx of x squared is 2x, and here again you have to apply the chain rule. The outer room here is the sine room, and the inner room is that function, whatever it is, y. So you differentiate the outer room keeping the inner room intact, that way you get cos y, and then multiply it by the derivative of the inner room, dy dx. Then you take this to that side. Whenever I say things like this, now take this to that side, that is just a way of expressing what we actually do. I mean, there is of course no physical movement involved with these quantities, that it goes from this side to that side. When I say you take this and push it to that side, I really mean subtract cos y dy dx from both sides, so that it vanishes on this side and appears on that side with a minus sign. That's the actual meaning. But anyway, so this is what you get. 2 minus cos y times dy dx equals 2x. And then when you divide both sides by 2 minus cos y, you get this expression. So whatever graph this equation has, the slope of that graph at any point x comma y is given by this function 2x divided by 2 minus cos y. Do you notice one more thing? You do not have to worry about 2 minus cos y being 0. It is never 0 because cosine value is never equal to 2.